On to the last objective of section 6.2, which is the mean and standard deviation. Now, because of the formulas for probabilities, it turns out that the mean and the standard deviation of a binomial random variable follow very specific, very simple formulas. Namely, that the mean is n times p, and the standard deviation is the square root of n times p times 1 minus p. And honestly, this is mostly due to, well, it's due to a couple things, but primarily it's due to the way binomial experiments are set up and how they work. But for whichever reason it is, it makes things so much simpler to not even have to bother with the sum product thing to be able to find your mean and your standard deviation. That's awesome. So for example, a statistical bulletin published by Metropolitan Life Insurance Company reported that 2% of all American births result in twins. So you get a random sample of 8,000 births. First thing, explain why this is a binomial experiment. Because it follows the follows the four principles of a binomial experiment. Namely, it has a fixed number of trials. You're looking at 800 births. So 8,000 births. 8,000 births. They're independent because, if one couple has twins, doesn't have any effect on whether the next couple has twins, right? Then you have success and failure. You either have twins or you do not have twins. There's no middle ground there. And then the chances of success is 0.02. I mean, if 2% of all couples have twins, then, 2% of all births are twins, then 0.02 is your chances of twins. And then probability of failure is 0.98, 1 minus 0.02. All right, now what's the mean and the standard deviation? Well, according to the formulas up at the top of the page, the mean is just n times p, which is 8,000 times 160. 8,000 times 0.02, which is 160. And the standard deviation is square root of n times p times 1 minus p. That's the square root of 8,000 times 0.02 times 0.98. And I just used a calculator or Excel to find that for me. All right, now interpret that. It means that we, in a random sample of 8,000 births, we expect 160 of them to be twin births, give or take 12.52. All right, done with that. That's been interpreted. Now, suppose a large metropolitan hospital claims that in their latest 8,000 births they had 200 twins. Is that unusual? Now, remember that in Chapter 3, we'd considered unusual to be past 2 standard deviations away. Now, this is on the high end, right, because it's 200. So we're not even going to bother with the negative numbers. We're just going to look at the positive ones. So we're going to take the mean and we're going to add on 2 standard deviations. So if you add on 2 standard deviations to that mean, take 160 plus 2 times 12.52, you get 185.04. As a matter of fact, if you add on 3 standard deviations, you get 197.56. So yeah, 200 would be very unusual because 200 is higher than 2 standard deviations away. As a matter of fact, it's higher than 3 standard deviations away. So it is quite unusual to have a hospital with that many twins. All right, done with that. Oh, I guess that wasn't the last objective. The last objective is some binomial probability histograms. So again, I didn't have you bother making these. If you wanted to make a histogram, here, I'll show you. All you got to do is highlight all your probabilities, insert column chart. Boom, you got a histogram. Simple as that. All you got to do from then on is just change your select data, edit your column labels from A2 to whatever, say OK, and there it starts at 0 now and ends up at 20. And of course, notice it's not that they don't exist over here at the 20 range. It's that they're so small that you can't really see it. And I hate that coloring choice. So I'm going to pick something else. Ugh, I don't even like gray either. How about that? There we go. Okay, so you can see what happens here. Over here, it's not 0, but it's really close to 0. It's That's scientific notation over there. See that E negative 27? That means it's 26 zeros and then a 9. It's 26 times, right? Which is really darn small, okay? So it's too small for the computer to graph. The computer is losing it about, well, 5. It shows a little sliver, 6, 7, 8, and 9, and so on, okay? So that's how to draw one of these histograms. Yes, you can do it and should do it in this spreadsheet for yourself. Speaking of which, this is the end of our spreadsheet, so I might as well save it because I don't think we're going to need this anymore for anything else. So we put in a histogram. We now proved ourselves. We know how to do what we learned in chapter 2, how to make a histogram. There they are. And how to change those labels and make the gaps all disappear. All right, so let me go back here and let's look at this. So these are histograms that are pre-drawn for you, and your job is to figure out which one was the 0.8, which one's the 0.2, and which one's the probability of success is 0.5. So you look at the 3 of them, ponder that for a second, and let's look at the top left graph right here, this one right here. Let's think about that. This one I'm going to tell you right now is 0.8. Now here's why. If the probability of success is 0.8, that means that you're going to have a lot of successes, right? That's the high probability of success. Because, of course, the largest a probability of success could ever be is 1. You can never have probabilities higher than 1. So if your chances of success are high, that means you're going to have a high number of successes, right? So most of, or the bulk of what you're going to see is going to be over here on the right, on the high side. Another way to see it is that the mean is the balance point, right? We learned that in chapter, literally, the first day of class, right, for many of you, 3.1, right? So you multiply, for our purposes, because this is a binomial, 15 times 0.8, n times p, np, which is equal to 15 times 0.8, which is 12. That's the balance point. That's the seesaw point, right, the fulcrum. Well, look at 12 right here. Look. Half of it's on one side, half of it's on the other. This thing would balance out on 12, okay? And similarly, that's how you know that this one has to be 0.2. 0.2 is low for the probability of success. So you're going to have the lump of stuff on the low side, and just a little tail going off to the right. Okay? Another way to put it is that the mean would be 15 times 0.2, which is 3. And that's why 3 is the balance point for this one. If you want to see it right here. Right there is the balance point. Okay. Now down here, this one's 50-50. The probability of success is 0.5, and look how perfectly symmetrical the thing is, right? Because the middle should be 7, right? Or 7.5, right? So, because it's 15 times 0.5, which is 7.5. And that's why this thing perfectly balances out on either side of 7.5. If we look at the one we did in here, look at that. Our chance of success was only 0.05. Look how tiny that is. And that's why the lump of it is over here on the low end, because that's a low probability of success. If it was 0.95, it would hop over to the right and the lump would be over here on the right. But it wasn't. It was 0.05. I'm saving it again. Saved. That way when I submit it later, everything will be good. All right, now the other graphs work similarly. That's what I was just explaining. The lump over here on the low end because probability is low. Here the lump is in the middle. The high points are in the middle because 0.5 is right in the middle. Now, let's look at the 0.2 one again, this one right here with the left. See how it's all on the left? So I drew that one with 3 different n values, right? So I drew one with n is 15, n is 30, and n is 70. So here's 15, here's 30, and here's 70. Look at that. What do you notice? Poof. Look at this last one. This is really important to you. And we'll talk about it more a little bit in chapter 8 and 9 and 10. But the fact is that if you get a big enough sample, right, like this is, do you see what happens to the distribution? It becomes normal. So notice how in this last distribution where n was 70, it's very normal and bell-shaped. This is important to us. So if n is large enough, then the binomial distribution becomes more and more normal, right? Now, how large is large enough? Well, differing books differ. Like, so every textbook you get would say a slightly different answer. But for our purposes, we're going to follow what's down here in the bottom box. Namely that n times p times 1 minus p has got to be greater than or equal to 10. Which in our case, I put it right here. N times p times 1 minus p was 70 times 0.2 times 0.8. That's 1 minus 0.2. And that was 11.2. And again, I just used Excel or a calculator. And notice how that's bigger than 10. That's why this curve is basically normal. That's not exactly normal because it's discrete still. A normal curve is technically a continuous distribution, which we'll learn about in chapter 7. But that's the deal. Like, if you have a big enough n, you can sort of treat your discrete distribution like it's continuous, even if it wasn't. And that's going to help us out a lot when we start dealing with polls and surveys, remember, because the binomial thing is really only useful for dealing with, well, it's useful for a whole bunch of stuff, but it's very useful for dealing with polls and surveys. Like, are you approving of the president's job performance, or are you not approving, that kind of thing. So that kind of poll is really binomial. But if you get a big enough sample, like 1,000 people, then you can treat it more or less like it's continuous and normal. And that's what we'll deal with in chapter 8. And I wrote it down here. So this whole n times p times 1 minus p is a big, big, big deal. It's going to allow us to use normal distributions for all sorts of binomial things, i.e. surveys and polls, when we get to chapters 9 and 10 and 11. All right, with that, we are done with chapter 6. I will see you back here for chapter 7, which is when we will deal with that curve that you're seeing right here, that normal curve, but without the boxes to make it. What happens when it's just a smooth, continuous curve? Right, we'll work with that later on in the next set of videos. See you then.